Hey y'all, welcome back to another round of astronomy. And yeah, let's get at it. What you're looking at in front of you is the bullet cluster. And hopefully by the end of this lecture, this picture will make more sense to you why it's important and why I've included it in the slides. So let's get going. First off, I have a question for you, namely a reminder question, a review question. So right here. Which of these two graphs below is consistent with Kepler's second law? So go ahead, take a minute, see if you can hack your way through that. Got it? Say good. And the first thing we have to remind ourselves is, what is Kepler's second law? The further you are from the sun, the slower the planet moves. As r increases, we should see the speed go down. So this one is not consistent with Kepler's second law. It's this one. As the distance from the sun outwards increases, your speed drops. Now, why did I point this out? Why did I bring this up? The issue is don't forget that Kepler's second law is based on Newton's law of gravity. Okay, number one, Kepler's second law has a basis in Newton's law of gravity. And so the interesting idea is that Kepler's second law, we could apply that to something else, say satellites orbiting the Earth. Although it was developed historically for the planets and the sun, because it has its underlying basis in Newton's law of gravity, we could take this idea and apply it to objects orbiting other objects. It doesn't necessarily have to be the sun and the planets. Okay? I want to make sure you kind of latch onto that idea. That's an important idea that we'll use in the next slide. Okay? So, now we're not going to apply it to planets orbiting the sun. I mean, we did that earlier, but we're not going to do it here. Okay. What I would like to actually look at is stars orbiting the center of a galaxy. Okay. So the same idea should apply, is that when stars orbit the galactic center, as we move further from the center, we should see the speed of those stars decrease. As a reminder, I have here an image of a galaxy and the redshift and or blue shift of the galaxy. Now remember, I gave you this picture when we had the Doppler effect introduced, but we have two ideas being presented in this bottom graph. The first one is the redshift of the galactic center. Okay, that would be right here. And by that redshift, you can figure out how quickly the center of that galaxy is moving away from us. But in addition to that, you see with respect to the galactic center, some stars are shifted towards the long wavelengths, the redshift, and you have other ones that are blue shifted with respect to the galactic center. And in that way, we get an idea about the rotation of the galaxy. So we have an idea about how to get the rotation of stars around the galactic center. Now couple that with Kepler's second law, and now we'll get an idea about some issues. You ready for it? Wow. Now let me explain what you're looking at. Okay? On the horizontal axis, you see radius given in kiloparsecs. On the vertical axis, you're seeing the rotational speed. What that means is the speed of a star going around the galactic center. Okay? And immediately what you notice is that, okay, you get this peak, but unlike Kepler's second law, what we would expect for Kepler's second law is the peak to start dropping. Okay, getting closer to zero as you get further away from the center. But you notice that at first it starts dropping, but then all of a sudden something goofy happens. It actually goes up, sort of levels out. That seems weird. Now, this is for the Milky Way galaxy. Maybe it's just us. Maybe we're the oddball and there's other galaxies that, are okay. No. Okay. This is actually for the Andromeda galaxy. And again, you notice that after some peak and a drop, then it goes back up. And that's the weird thing, is that it seems, no matter what galaxy we're looking at, or by and large, most of the galaxies we actually look at don't seem to follow Kepler's second law. And don't forget, Kepler's second law is, you can get that from Newton's law of gravity. So it seems to indicate that there's something wrong with our conceptualization of gravity. So this is the first hint that we don't have a complete model. And bear in mind, we're up to 2020s now. Okay, we have fast forward. Granted, these problems have known since the 1980s. This one's 1970. Okay. So this is the first hint that we don't have everything included in our model. Pretty cool. Okay. So that brings me to the bullet cluster. Now here is a false colored image. You notice it was taken with Chandra, the X-ray observatory. Okay. And it's falsely colored so that white corresponds to regions emitting a lot of X-rays, and blue are regions that don't emit very much X-rays. Okay. Now, you notice the specific shape. You see that there seems to be a region right here and another region right here where there seems to be particularly hot regions of gas. What you're actually looking at is a galactic collision. You have two galaxies that are passing through each other. And the two regions that are emitting the most X-rays, right here and right here, those would correspond to the center of those two respective galaxies, okay, the most dense regions. Now, what's going on here is that during this quote-unquote collision, as these two galaxies pass through each other, the little particles of dust that are comprised of those two galaxies, they start running into each other. They start heating up. So you have this increase in temperature of the dust. We generally interpret this image as showing us where the gas, the dust, is the most dense in this collision process. The high X-ray emitting regions, more dense gas, more material. The low emitting regions, less dense gas, less material.
Go to the center of gravity's pull and find your planet, you will. Yes, yes. Many planets you will find.
But that's the idea. That's exactly what we need to do. Okay? So we have an idea about where the material is. But we can also look to see where gravity's pull seems to be located. And this is the cool thing. Okay? Let me walk you through this. You're probably familiar with the topographical map, right? Lines on a topographical map give you constant elevation. You can think of this as also being a topographical map, except here, the lines indicate a constant gravitational pull. And just like a topographical map, you can locate where the center peak or valley happens to be. Now, overlaid on this is that X-ray image that I showed you previously. Take a minute, pause. What seems funny about this image? You see it, right? It's cool. Look, the place where the material is located, here and here, doesn't align with the location of the gravitational pull. It's almost as if there is some material which does not emit light, but exerts a gravitational pull. Huh. So we have two problems. We have two issues. Now, you know, as good scientists, when your model conflicts with your observation, which one do you have to modify or throw out? The model. We have to modify our model. We have to modify it with something that doesn't emit light. So we'll call it dark. And something that interacts gravitationally. Well, we'll call that matter. So astronomers are very fancy, right? And if we can include this dark matter in the galaxy, then we can fix the rotational curve problem. And we can answer this issue that the Bullet Nebula presents. Let me give you an idea of how we do this. So what I'm going to do is open up a web page. This is just a screenshot. Let me go ahead and move over the web page. Okay. Now let me walk you through what each of these slider bars does. Okay. The first one, the bottom one, is the one I'm going to play with first, and it says disk mass to light ratio. What this means is that we generally estimate the mass of a galactic center based on how much light is being produced. So what this slider bar allows us to do is to say for 1 unit of solar luminosity, how much material must be present. And you can see that we can adjust this all the way up to 5. And notice we're recovering that characteristic shape that we would expect from Kepler's law, is that as you move outwards, okay, we have to get outside the galactic center before we see this decrease as we move further and further away. So right about here, 5 kiloparsecs or so, then you notice it starts declining, like we would expect according to Kepler's laws. And you notice that no matter what value I set at, I can't match the observed data. Those are the blue dots. Doesn't matter, right? I need to add in additional material, mass, which does not emit light. Well, how do I do that? That's the next 2 slider bars. Okay. So one of these, you notice it says halo core radius. So this halo core radius tells us how far into the disk of the galaxy, if you will, this dark matter spreads. And the halo central density is telling us how much dark matter is present per, you notice here, cubic parsec. Okay. How many solar masses of dark matter do I need per, 10 cubic parsecs of space? Okay. So we can do something like, okay, let's go ahead and make this, 200 solar masses. And right now we say that that extra 200 solar masses per 10 parsec cubed, okay, has a radius of 0. It doesn't extend anywhere. Now, as we take that region and we extend it outwards, now you notice the orange line is the gravitational effects due only to dark matter. The green line would be the gravitational effects due to luminous material. In other words, stars, gas, dust, things that we can actually see emitting light. And then the red is the total, the combined of both of the green and the orange line. We'll see if we can match the observations. So now I'm just playing with the slider bars. Okay, that's too much. That's not enough. So you can kind of get a sense of playing with the slider bars and comparing it to the observed data, roughly how much additional material that we don't see is actually needed to match our observations of the speed at which the galaxies rotate. Okay? And we think that according to this little model I'm doing online here, this would mean that that material, that dark matter, would have to extend about 1 kiloparsec from the center of the galaxy outwards in order to present enough mass so that the gravitational orbits of the remaining stars align with what we observe. So this is where we modify our model. We incorporate additional material. Pretty cool, huh? Play around with that. See if you can get a better value than I can. I'm sure you can. We think that a galaxy is about 15% luminous material. About 15% luminous material, and about 85% dark matter. It's kind of weird to think about. When you see a picture of the Andromeda Galaxy or the Milky Way Galaxy or the Sombrero Galaxy or whatever galaxy, most of that galaxy in terms of gravitational influence, about 85% ballparkish, is material that doesn't emit any sort of light that we know of. It only interacts gravitationally. Here's how we get an idea about where dark material is, dark matter. Okay? If we know what an object should look like, for example, we know that each of these are a nice little pinprick of light. If we know what they should look like, and then what they appear to look like, we can get an idea about the material between us and that object. The warping of the shape of that object tells us something about the mass that is between us and that object, even if we can't see it. We are looking at the gravitational effects on light. So this is how we map out dark matter. We take, for example, Hubble. We collect what the shapes of galaxies look like. And knowing what a spiral galaxy should actually look like, we can reconstruct how much material, gravitational material, is between us and that galaxy. Let me give you a larger survey. Okay? And here's a quote. Okay? We have been able to measure the shape of each galaxy, how distorted it is, with extremely high precision, about 1 part in 1,000. What you see is that the red areas are places where there is a lot of gravitational material, and the blue areas are where there is not very much gravitational material. And so we can start getting an idea about where there's a lot of dark matter and where there isn't very much. Incidentally, there's a slightly larger survey, and I'm sorry, I must have gotten rid of that slide. Let me put it up for you. There you go. And I would say, what does this thing look like to you? Now, ignore the color schemes, that kind of thing, but what does this distribution of dark matter seem to resemble to you? I don't know about you, but to me, it kind of reminds me of the CMB, right? The cosmic microwave background. If you remember, we said the cosmic microwave background essentially represents small differences in temperature in the very early universe. Well, the very early universe, those small differences in temperature mean small differences in density. We would expect that if we take those densities and we run forward in time, we would expect to see clumping of some galaxies, and other places we won't see galaxies. And the size of that clumping from the Planck measurements, the Planck CMB measurements, the size of the clumps in this Planck measurements, we would expect to roughly be the same as the size of these clumps of dark matter. So there's a prediction. If we can map out the dark matter, we would expect the average clump size, if you will, to resemble the average clump size on the cosmic microwave background. Hey, I hope that keeps you thinking. Thanks for your attention. I'll see you next time.